All right, welcome to section 11.2. In 11.2, we're talking still about limits, but we're talking about some actual techniques for you to evaluate limits. So if you did that 11.1 homework, you probably noticed that like a lot of times when we were looking at tables or when we were looking at graphs, it was like, I don't know exactly what that is. And some of you really struggle with that. You're like, I want to know that it's 391sts in the first place. Like, how do I get that 391sts? I hope you didn't get any problems that had that because you shouldn't have. And that's what we're going to be talking about in this section is how do we sort of more algebraically come up with those limits? So in this section, we're learning about the techniques other than graphing and using a table in order to evaluate limits. So the first technique that we're going to talk about is reduction. So when we're talking about the reduction technique, it's always of a rational function. And it's really just dividing out the factor that is an issue. So what we're going to say here is f of x is equal to n of x over d of x, which is equal to then q of x. So if we have a function that is written as the quotient of two functions, then the function is equal to whatever you get when you divide those two functions by each other. And if n of x and d of x share a common factor, so the numerator and the denominator have some factor in common, then that factor can be canceled so that it reduces to just q of x. And that might seem confusing, but I promise you, you've actually done it. You did it in chapter 2. Thus, the limit as x goes to c of f of x is equal to the limit as x goes to c of q of x. And what we're just saying here is if I have some rational function where there is a shared factor that can be divided out, then taking the limit of that rational function is going to be the same as taking the limit of the quotient of that rational function. So, for example, if we have f of x is equal to x squared minus 4 over x plus 2, if I wanted to talk about, and we'll deal with this in a little bit, if I wanted to talk about the limit as x goes to negative 2, the first thing we always do is just substitute it in real quick. If I substitute negative 2 into this, I would get 0 on top over 0 on bottom. So that's undefined. But that's what the function is equal to. The function is undefined at negative 2. The limit, not necessarily. And this is where we can use reduction. So x squared minus 4 over x plus 2. I can factor this as x plus 2, x minus 2 over x plus 2. And now my x plus 2's can cancel. So when I actually do the division of these functions, I get x minus 2. Which means that when I have the limit of that rational function, that's equal to the limit as x goes to negative 2 of the quotient function, x minus 2. And you can see here, now if I substitute this negative 2 in, I have negative 2 minus 2, which is negative 4. When we're dividing this out, when we get that 0 over 0 and a factor cancels, this is what's telling me that there's a hole in the graph. So now if I were to look at these two graphs, if you wanted, go to your calculator and graph this as y1 and graph this as y2. What you're going to get is really just one line that looks not like that because my tool didn't do what I wanted it to. So you're going to get one line that looks like this. This equation is the same. We're saying these two things are equal. The only singular difference between them is whether or not at negative 2, the point negative 4 is on the function. Here, in y2, negative 2 comma negative 4 would be a point on that. But in the original function, this would actually just be a hole right here. The limit, however, when I'm talking about a limit, what am I going towards? From the right, I'm going towards the y value of -4. From the left, I'm going towards the y value of -4. So the overall limit is still -4. And we were able to do that and find that algebraically by canceling off those factors. All right, so when you plug in and get 0 over 0, so this case, 0 over 0, most likely the limit is going to exist. Now, this isn't always the case. You can get 0 over 0 and still not have a limit. But generally speaking, you usually do. This situation is called the indeterminate form. So the indeterminate form is 0 over 0. And what it tells us is that the numerator and denominator may have a common factor. That common factor is the thing that's creating a hole in the graph. All right, so here we have a whole bunch of examples. I'll do those in the examples video. I don't want to bore you. Rationalizing technique, so a different technique. If a function contains an irrational term, what you want to try and do is rationalize that. So for example, if I have f of x equals root x minus 2 over x minus 4, and then I try and take the limit as x goes to positive 4, first substitute that in. Square root of 4 is 2, minus 2 is 0. 4 minus 4 is 0. So I have the indeterminate form. Now, there's no common factor here necessarily. So what I'm going to do is rationalize this. I'm going to show up here how I rationalize this. We learned way back when, if you multiply by the conjugate, so the conjugate is when I'm just changing that middle sign, what that's going to do is rationalize the numerator. And usually you're not like thinking about rationalizing the numerator because you're like, no, you got to rationalize the denominator. All we're doing is rationalizing the numerator so that we can cancel something. And you'll see how that looks. If I multiply the numerator out now, square root x times square root x gives me x. -2 times 2 gives me -4. Remember that because it is a conjugate, you don't need to multiply outside inside, because in a conjugate, those would always end up canceling. In the denominator, I am not going to multiply this out. I'm just going to leave it as x minus 4 times square root x plus 2. And the reason I'm not going to multiply it out is because what I want is to have something that can then cancel. So I'm left with 1 over square root x plus 2. So now where I had 0 over 0, if I want to find the limit as x goes to 4, I can take the limit of this rationalized function and take 1 over, the limit as x approaches 4 of 1 over square root x plus 2. And if I substitute that 4 and I get 1 over 2 plus 2, which is 1/4. So now I know what that function is going towards as I get closer and closer and closer to 4. Without looking at a graph, without looking at a table. What I know about this graph, however, is the coordinate 4, 1/4, 4 for my x, 1/4 for my y, is not on the function. That is where there is a hole. But the limit is still 1/4, because the limit is what I'm going towards, not what I algebraically get by substituting that point in. Okay, we've got some more examples and some more examples, and then we're going to talk about one-sided limits. So we talked about it in section 11.1, where I was talking about, the limit from the left and the limit from the right, but we actually have notation that says that. If we wanted to talk about the limit as x approaches c from the right, what we do is we write that as limit as x is going to or approaches c, but then we put that little plus here. That's not like an exponent. I'm not raising it to the positive. That's just indicating that I'm talking about the limit as I am moving from the right of a graph. If I put a little negative up there, I'm not raising it to the negative power. It doesn't mean inverse or reciprocal or anything like that. All that is telling me is I am moving from the left side of this graph, going towards whatever x value or c value that I am looking at. So in order to have an overall limit, so that's how I'll refer to this, the existence of a limit. And when we're talking about that, we're talking about an overall limit. The limit as x goes to c of some function is equal to L if and only if the limit from the right is equal to the limit from the left, which is equal to some number L. So keep in mind, if I said that the limit from the right does not exist and the limit from the left does not exist, then that's not equal to some number L. What I have to have happen is the limit from the right be equal to the exact same value, a numeric thing, as the limit from the left, in which case there is an overall limit at C of L. And we'll get some examples dealing with that. And then we have these difference quotient questions. I'm just going to throw it in here right now. It's a short notes video. Please go and watch these. Even if you just watch these, scroll to the end and watch these. I said back in the beginning of the year, back when you first started hearing my voice in chapter 2, that the difference quotients was going to come back and it was going to be a little bit vengeful. This is where it comes back, and it's a little bit vengeful because you don't remember it, and it's a little bit tough, and now we're also including limits into it. So just go, hear my explanation. It's not going to hurt you. It can only help you. All right, other than that, that's it for section 11.2. Go watch that examples video.